Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're covering chapter 5 in our physical chemistry playlist, and this chapter focuses on Gibbs free energy and phase equilibria. In this chapter, we're going to cover the following objectives. First, we're going to define Gibbs free energy and explain what it tells us about spontaneity. Second, we're going to explore standard molar Gibbs energy of formation and how it's used in thermodynamic calculations. Third, we're going to examine how Gibbs energy depends on both temperature and pressure, and that's going to be important when we're analyzing chemical and physical processes under different conditions. Finally, we're going to dive into phase equilibria, including the Clapeyron and Clausius-Clapeyron equations, as well as how to interpret phase diagrams. With that, let's go ahead and get started. Up until this point in our course, we've introduced and explained in great detail the first and second laws of thermodynamics. The first law taught us that energy is conserved. Energy can neither be created nor destroyed. It may change form from heat to work or from potential to kinetic energy, but the total energy of the universe remains constant. The second law then introduced a deeper idea. It told us that not every process that conserves energy will actually occur. So the second law helps us determine which processes are spontaneous and in what direction they naturally proceed. And it did this by introducing a new quantity, entropy. And entropy measures the dispersal of energy. In addition, we've talked about the change in enthalpy, which we interpret as the heat content of a system under constant pressure. Together, enthalpy and entropy describe the two competing tendencies in nature, one that drives systems towards lower energy and another that drives them towards greater disorder. Now, up to this point, we might expect that we already have enough thermodynamic quantities to deal with any situation. And that expectation isn't entirely wrong. But the equations we've developed so far aren't always the most convenient to apply. Yes, we know how to calculate the change in entropy for both the system and the surroundings. But let's be practical. We're generally interested in what happens to the system. That should have us thinking about how we can establish criteria for spontaneity and equilibrium in terms of the change in a specific thermodynamic function of the system, without having to worry about those darn surroundings or the universe as a whole. So how do we connect energy and disorder into a single framework that allows us to predict whether a process will happen spontaneously? That's exactly what the concept of Gibbs free energy accomplishes. Free energy. Don't let the US government get their hands on this, but it gives us a single elegant criterion that tells us not only whether a process is spontaneous, but also the direction in which spontaneous change will occur. And beyond that, it forms a vital link between the laws of thermodynamics and the behavior of both chemical and physical equilibria. Now, to see how this emerges, let's start again from the second law. The second law says that for any real process, the total entropy of the universe must increase, or in the limiting case of a reversible process, remain unchanged. In differential form, we can write this as the change in the entropy of the universe equals the change in the entropy of the system plus the change in the entropy of the surroundings, and this total must be greater than or equal to 0. Now, because the surroundings are usually modeled as a large thermal reservoir at temperature T, the infinitesimal change in their entropy can be written as the heat they exchange divided by their temperature. If we denote the infinitesimal heat transferred to the surroundings as dq surroundings, then ds surroundings equals dq surroundings divided by T. But any heat that the system gives up, that's what's gained by the surroundings, which means dq surroundings is equal to the negative of dq system. So substituting that into our expression gives us ds universe equals ds system minus dq system divided by T. And this must be greater than or equal to 0. Now let's consider that the process occurs at constant pressure. Under this condition, the heat exchanged by the system is equal to the differential change in enthalpy, dH system. Replacing the heat term then gives us ds system minus dH system divided by T is greater than or equal to 0. Now, if we multiply through by negative T, we're going to flip the inequality and obtain dH system minus T times ds system is less than or equal to 0. This inequality is the key. It suggests that there exists a particular combination of enthalpy and entropy that remains constant at equilibrium and decreases for spontaneous processes. That combination is what we call the Gibbs free energy. We define it formally as G equals H minus T times S. Now this definition, it may look simple, but it carries enormous physical meaning. The Gibbs free energy represents the portion of a system's total energy that is available to perform useful work when both temperature and pressure are held constant. It ties together the competing influences of enthalpy, which favors energy minimization, and entropy, which favors disorder, all into a single measurable quantity. Now let's see what happens when the system undergoes a small infinitesimal change. Taking the differential of the Gibbs function gives dg equals dH minus T ds minus S dt. For a process that's carried out at constant temperature, we know dt is going to be 0, so that last term actually vanishes. We're left with dg equals dH minus T ds. This equation becomes our practical criteria for spontaneity. If the change in Gibbs free energy for the system, dg, is negative, then the process is spontaneous in the forward direction. If dg is positive, the process is non-spontaneous under those conditions, and if dg equals 0, the system is at equilibrium. The beauty of this is that it allows us to evaluate spontaneity without having to track the surroundings explicitly. The information is fully contained within the system itself. Since we often deal with finite changes rather than infinitesimal ones, we can write the same relationship using finite differences. So we can write delta G equals delta H minus T times delta S. This is the Gibbs free energy equation that will guide us through much of this chapter. Now, how do we interpret this equation? What does the sign of delta G actually tell us? If delta G is less than 0, the process is spontaneous under the given conditions. That means it's thermodynamically favorable. It will proceed without additional energy input once started. If delta G is greater than 0, the process is non-spontaneous under those conditions. So energy has to be supplied continuously for that process to occur. And if delta G is equal to 0, the system is at equilibrium. The forward and the reverse reactions are happening at equal rates, and there's no net change in composition. You can visualize this with the two diagrams that are shown here. So on the left is an exergonic process. The reactants, they begin at a higher free energy than the products. And the curve drops as the reaction proceeds. Now, the height of that drop represents the change in Gibbs free energy. And because the final state is lower, delta G is negative, and this reaction is spontaneous. On the right is an endergonic process. This time, the products are higher in energy than the reactants. So the curve rises overall. That means delta G is positive, and this reaction is not spontaneous under the given conditions. Here, I really want to point out, again, that neither enthalpy nor entropy alone can tell us if a process is spontaneous. A process with a favorable delta H might still be non-spontaneous if delta S is unfavorable and temperature is high enough. Likewise, a favorable entropy change might be overridden by a large positive delta H. And only by combining both terms in the Gibbs equation can we predict whether a reaction will actually happen without additional energy input once started. Now, to help with this, we can use this summary table, which organizes the outcomes of spontaneity based on the signs of delta H and delta S. Let's walk through each of the 4 combinations in this table. When both delta H and delta S are positive, the reaction is spontaneous at high temperatures because the T delta S term becomes large enough to make delta G negative. When delta H is positive and delta S is negative, the reaction is going to be non-spontaneous at all temperatures because both terms contribute to making delta G positive. When delta H is negative and delta S is positive, the reaction is spontaneous at all temperatures because both terms make delta G negative. When both delta H and delta S are negative, the reaction is going to be spontaneous at low temperatures because the minus T delta S term becomes less significant. Now, the trends in this table, they can be a lot to memorize. A way to remember them is just to understand the equation. So let's play around with some fake numbers so that we can understand each one of these scenarios. Let's say that our delta H is equal to 100 and our delta S is equal to 2. We're not going to worry about units here. We're going to pretend they all cancel out all in the right way. We're just looking at whether delta G is ultimately going to be positive or negative. Now, one comment I want to make is temperature has to be in Kelvin, which means the lowest temperature T can be is 0 Kelvin. That helps us determine a lot about the minus T delta S term, whether that's going to be positive or negative overall. Okay, keep that in mind. Let's play with some numbers. In our first scenario, let's say delta H is equal to positive 100 and delta S is equal to positive 2. If we want this reaction to be spontaneous, it will only be this case if temperature is high enough. Let's work this out. Let's write this out. Delta G is equal to 100 minus 2T. The only way that our TS term is large enough to be subtracted from 100 and give us a negative delta G is if temperature is greater than 50 Kelvin. If it's any lower, we're going to get a positive delta G, which means non-spontaneous. So whenever you see a positive delta H and a positive delta S, it will only be spontaneous if temperature is high enough so that the TS term is large enough to be subtracted from our delta H and still give us a negative delta G. Now let's say that delta H is positive 100 and delta S is negative 2. Because temperature is in Kelvin, it can never be a negative number. So that means if we look at this minus TS term, S will be negative, T will be positive, and we obviously have this minus sign out front. So we're multiplying minus times positive times minus, or negative. This is going to give us an overall positive number. So we have a positive delta H plus a positive term. That's always going to give us a positive delta G. There's no value of temperature here that will give us a negative delta G. So for this combination of positive delta H, negative delta S, the reaction will always be non-spontaneous at all temperature. Next, let's look at a negative delta H and a positive delta S. So let's say delta H is negative 100 and delta S is positive 2. At any temperature, our minus TS term is going to be negative since T and S are both positive. So we will have a negative number minus another value. So that means our delta G term will be negative at all temperature. Considering delta H is also negative, all temperatures will give us a negative delta G. Last, let's say that delta H is minus 100 and delta S is minus 2. So in this case, the minus TS term will actually be positive. So we'll have negative 100 plus 2T. In order for us to get a negative delta G here, temperature cannot be larger than 50 Kelvin. That means we need low temperature. So this is why for the combination of a negative delta H and a negative delta S, we say that the reaction can only be spontaneous at low temperature. Now, before we move on, there is one last thing I want to point out, and this causes a lot of mistakes on homeworks and exams, and that's unit consistency. Enthalpy values, they are usually given in kilojoules per mole, while entropy values are often in joules per mole per Kelvin. So if you're calculating delta G and you don't convert the units properly, your answer is going to be incorrect. It's going to be off by some factor. So always make sure that both terms in the Gibbs equation have the same units before you plug them in and calculate. Okay, now most of the chemistry we study, we've said, especially in lab environments and biological systems, take place under conditions that are fairly close to constant temperature and constant pressure. And under those conditions, the Gibbs free energy helps us determine whether a process will occur spontaneously or not. We've already introduced the equation for this. Gibbs energy equals enthalpy minus temperature times entropy. But what does this actually mean? Beyond helping us evaluate spontaneity, this equation also reveals something deeper. It gives us insight into how much useful work a process can potentially perform. To unpack this more rigorously, let's consider how Gibbs energy changes during an infinitesimal transformation. If we take the total differential of the equation G equals H minus T times S, and we apply the product rule to the temperature entropy term, we get that the change in Gibbs energy equals the change in enthalpy minus temperature times the change in entropy minus entropy times the change in temperature. Now let's also express the change in enthalpy. Enthalpy is defined as internal energy plus pressure times volume. So when we take the differential of that relationship, we get that the change in enthalpy equals the change in internal energy plus pressure times the change in volume plus volume times the change in pressure. Now we need an expression for the change in internal energy. By the first law of thermodynamics, internal energy changes due to both heat and work. In differential form, the change in internal energy equals heat added to the system plus work done on the system. If the only work being done is expansion or compression, then that work term becomes negative pressure times the change in volume. So we can write that the change in internal energy equals heat minus pressure times the change in volume. Now, if the process is reversible, We can also say that the heat added equals temperature times the change in entropy. And that substitution gives us that the change in internal energy equals temperature times the change in entropy minus pressure times the change in volume. Now we can substitute this result into our earlier equation for enthalpy. That gives that the change in enthalpy equals temperature times the change in entropy minus pressure times the change in volume plus pressure times the change in volume plus volume times the change in pressure. Notice that the two pressure volume terms cancels out and they leave the change in enthalpy equals temperature times the change in entropy plus volume times the change in pressure. Now we return to our expression for the change in Gibbs energy. Substituting in the expression we just found for the change in enthalpy, we can get that the change in Gibbs energy equals temperature times the change in entropy plus volume times the change in pressure minus temperature times the change in entropy minus entropy times the change in temperature. Here, the temperature entropy terms cancel out, and we're left with a very powerful result. The change in Gibbs energy equals volume times the change in pressure minus entropy times the change in temperature. So this result gives us a precise way to understand how Gibbs energy responds to changes in pressure and temperature. If the pressure increases, Gibbs energy increases proportionally to the volume. If the temperature increases, Gibbs energy decreases proportionally to the entropy. But it's also important to keep in mind the assumptions behind this derivation. It only holds when the system is performing expansion or compression work, meaning the work done arises solely from the volume changes against an external pressure. If the system is doing any other types of work, like electrical work, then this expression has to be modified to include additional terms. That said, the physical interpretation of Gibbs energy is even more powerful. So under conditions of constant temperature and constant pressure, any decrease in Gibbs energy corresponds to the maximum amount of non-expansion work that the system can perform. With that, we have completed objective 1, and we're ready to tackle objective 2, which is titled Standard Molar Gibbs Energy of Formation. The standard molar Gibbs energy of formation, written as delta G F naught, is the Gibbs energy change that occurs when we form 1 mole of a compound from its elements, with everything in its most stable standard state. Now, by convention, the standard Gibbs energy of formation for any element in its reference form is defined as 0. This is simply a choice of reference, and it sets a baseline so we can measure everything else relative to it. So for example, for oxygen gas and for graphite, which is the most stable form of carbon, delta GF naught equals 0. These aren't reactions that release or consume energy, they're the starting points. We only assign non-zero delta GF naught values when a compound is formed from these elemental reference states. Now, why do we use this quantity in the first place? Well, the absolute value of Gibbs energy for a substance, meaning the total free energy stored in it, can't be measured directly. Gibbs energy, like internal energy or enthalpy, is a state function, but only differences in Gibbs energy are physically meaningful or measurable. So to make consistent comparisons, we define a relative scale where elements in their standard states have a delta GF naught value that is equal to 0. Quick reminder here that this same rule applies to enthalpy as well. The enthalpy of formation for any substance in its standard state is defined to be 0. You've seen this in general chemistry. Anyway, once we've established that baseline, we can determine delta GF naught for compounds experimentally. This is done by measuring the Gibbs energy change for a reaction that forms the compounds from its elements. Those experimentally measured values populate the tables that you see in textbooks or databases, and that's how we get a full library of delta GF naught values, all referenced to the same 0 point. With those tables, we can then calculate the standard Gibbs energy change for any reaction as long as we know the balanced chemical equation and the delta GF naught values for all the species involved. So how do we actually calculate it? There's 2 equivalent approaches. The first is to use the formation values directly. This method is often the fastest. You take the sum of the standard Gibbs energies of formation of all of the products, each multiplied by its stoichiometric coefficient, and then subtract the sum of the standard Gibbs energies of formation of all of the reactants, also multiplied by their coefficients. So in other words, the change in Gibbs energy for the reaction equals products minus reactants, with each term weighted by how many moles are involved in the balanced equation. The second method is a bit more involved, but it's useful when you don't have direct delta GF naught values. Instead, you can use enthalpy and entropy to calculate Gibbs energy. So first, you calculate the standard enthalpy change of the reaction by summing the standard enthalpies of formation of the products weighed by their coefficients and subtracting the sum of the reactants weighed by their coefficients. And then you do the same thing with standard entropy values to find the entropy change of the reaction. Finally, you plug those into the thermodynamic equation. Delta G reaction naught equals delta H reaction naught minus T times delta S reaction naught. Here you need to remember that temperature needs to be in Kelvin. And if you're mixing units like kilojoules for enthalpy and joules for entropy, you need to convert to be consistent. So let's try an example. Let's say we're asked to calculate the standard Gibbs energy change for the combustion of graphite. The reaction is carbon in the form of graphite reacts with oxygen gas to form carbon dioxide gas. In addition, we're told that the standard enthalpy of formation for carbon dioxide is negative 393.5 kilojoules per mole, and the standard entropy of the reaction is 2.9 joules per mole per Kelvin. How do we tackle this problem? First, let's really look at the reaction. Notice that both carbon in graphite form and oxygen gas, they are in their most stable elemental states. So their standard enthalpies and their Gibbs energies of formation, those are all equal to 0. That means that the reaction has one product, carbon dioxide, and then 2 reactants with 0 formation energies. That makes the calculation for delta H reaction naught super easy. It's just going to be equal to negative 393.5 kilojoules per mole. Next, we notice that we're given the standard entropy of the reaction directly. It's equal to 2.9 joules per mole per Kelvin, or 0.0029 kilojoules per mole per Kelvin. And we want kilojoules here so that it can match our delta H value. We also have temperature, 298 Kelvin. So that means we know all 3 variables that are required for us to use our Gibbs free energy equation. We plug them in, we calculate, and we get that the Gibbs energy change is approximately negative 394.4 kilojoules per mole. So the formation of carbon dioxide is highly spontaneous under these standard conditions. With that, we've also completed objective 2, and we're ready to move on to objective 3, which focuses on the dependence of Gibbs energy. Gibbs free energy is a function of both temperature and pressure, and we need to understand how changes in either of these variables affect it. So in this section, we're going to derive working relationships that describe how Gibbs energy changes with temperature, and we'll also derive working relationships that describe how Gibbs energy changes with pressure. Let's start by looking at how G depends on temperature when pressure is held constant. We're going to begin with the differential form we derived earlier, dG equals VdP minus SdT. Now, if we're working at constant pressure, that dP term becomes 0, and that leaves us with dG equals negative SdT. That tells us if we plotted a graph of Gibbs energy versus temperature at constant pressure, the slope of that plot of that line is going to be equal to negative entropy. So in mathematical terms, the partial derivative of G with respect to temperature at constant pressure is equal to negative S. Now, we can substitute this relationship back into our Gibbs equation. Recall, Gibbs energy is equal to enthalpy minus temperature times entropy. If we rearrange that a little, we can express Gibbs energy as equal to enthalpy plus temperature multiplied by the partial derivative of Gibbs energy with respect to temperature at constant pressure. Now we're going to manipulate this further to find a more general expression. If we go ahead and we divide every term in that equation by temperature squared and then rearrange it, we get the following equation. This equation tells us negative Gibbs energy divided by temperature squared plus 1 over temperature multiplied by the partial derivative of Gibbs energy with respect to temperature is equal to negative enthalpy divided by temperature squared. Now, at first glance, this kind of looks complicated, but if you look just a little more closely and for a longer period of time, you're going to recognize that this combination of terms is exactly what you would get if you differentiated the ratio of Gibbs energy over temperature with respect to temperature. So we can simplify this entire expression into a much more compact form that says that the partial derivative of the ratio of Gibbs energy to temperature with respect to temperature at constant pressure is equal to negative enthalpy divided by temperature squared. And this is a super cool result. It tells us how the quantity G divided by T changes as temperature changes. So in other words, it means that the rate of change of the ratio of Gibbs energy to temperature is directly proportional to the negative of the enthalpy scaled by temperature squared. Now, so far, we've been discussing infinitesimal changes, but the same relationship also applies to finite changes. So in that case, we simply replace G and H with the corresponding changes for the reaction. So that gives us this final expression. The partial derivative of the ratio of the change in Gibbs energy to temperature with respect to temperature at constant pressure is equal to the negative of the change in enthalpy divided by temperature squared. This is known as the Gibbs-Helmholtz equation, and this equation lets us predict how the spontaneity of a reaction changes with temperature. Now that we've discussed how Gibbs energy depends on temperature, let's turn to its dependence on pressure. We'll start again from the general differential expression for Gibbs energy, which says that the change in Gibbs energy equals volumes times the change in pressure minus entropy times the change in temperature. If we keep the temperature constant, the term involving entropy and temperature disappears, and that leaves us with a much simpler expression. The change in Gibbs energy equals volume times the change in pressure. That tells us that at constant temperature, the slope of a plot of Gibbs energy versus pressure is equal to the system's volume. Or in derivative form, the partial derivative of G with respect to pressure at constant temperature is equal to volume. Now let's calculate how Gibbs energy changes when the pressure changes from initial pressure P1 to a final pressure P2. To do that, we integrate both sides of the differential expression. On the left side, we integrate the change in Gibbs energy, and on the right-hand side, we integrate volume with respect to pressure from P1 to P2. So, the total change in Gibbs energy equals the integral from P1 to P2 of volume with respect to pressure. For gases, we can make use of the ideal gas law, which tells us that the volume equals moles times the gas constant times temperature divided by pressure. Substituting this expression for volume into our integral, we get that the change in Gibbs energy equals the integral from P1 to P2 of nRT divided by P with respect to P, where N is the number of moles, R is the gas constant, T is temperature, and P is obviously pressure. Because N, R, and T are constants, for an isothermal process, we can pull them out of the integral, leaving us with nRT times the integral of 1 over P with respect to P. The integral of 1 over P is the natural log of P. So evaluating between P1 and P2 gives us that the change in Gibbs energy equals nRT times the natural log of the ratio P2 over P1. Now remember that a change in Gibbs energy simply means the difference between its final and initial values, G2 minus G1. So we can write that our result is G2 minus G1 equal to nRT natural log of P2 divided by P1. To make this expression more useful, we can introduce a reference point. In thermodynamics, it's often convenient to define a standard state, which is the set of conditions we use as a baseline for comparison. For gases, the standard pressure is chosen as 1 bar. So if we set the initial pressure P1 equal to 1 bar, and we call the Gibbs energy at that reference pressure the standard Gibbs energy, written as G naught, then our equation becomes G minus G naught is equal to nRT natural log P divided by 1 bar. Rearranging, we get the Gibbs energy at any pressure equals the standard Gibbs energy plus nRT times the natural log of the pressure divided by 1 bar. If we now express this in molar quantities, we simply divide through by the number of moles N. And that gives us that the molar Gibbs energy, written as G bar, equals the standard molar Gibbs energy, G bar naught, plus RT times the natural log of the pressure divided by 1 bar. This equation tells us that the molar Gibbs energy of an ideal gas depends on pressure through a logarithmic relationship. The standard molar Gibbs energy, on the other hand, depends only on temperature because it is defined at a fixed pressure, specifically 1 bar. Later in this lecture series, we'll see how a similar expression can be used to relate Gibbs energy not just to pressure, but also to the concentration of a substance in a mixture. With that, let's go ahead and jump into a practice problem. This problem says a 0.590 mole sample of an ideal gas initially at 300 Kelvin and 1.5 bar is compressed isothermally to a final pressure of 6.9 bar. Calculate the change in Gibbs energy for this process. Okay, so let's start by identifying what we're being asked for. We want the change in Gibbs free energy, delta G, for an isothermal compression. Since the temperature is constant and the gas is ideal, we can use the relationship we derived earlier. Delta G is equal to nRT natural log P2 divided by P1. This equation tells us how Gibbs energy changes with pressure for an ideal gas when the temperature stays constant. Now let's list out the given quantities. The number of moles N is 0.590 moles. The temperature T is 300 Kelvin. The initial pressure P1 is 1.5 bar, and the final pressure P2 is 6.90 bar. Plugging these into our equation, we get that delta G is equal to 0.590 moles times 8.314 joules per Kelvin per mole times 300 Kelvin times the natural log of 6.90 divided by 1.50. Before we plug this in, let's think about what we would expect conceptually. Since the gas is being compressed, its pressure increases. That means the Gibbs energy should also increase because compression makes the system less spontaneous, so it requires work input. So we expect delta G to come out positive. And in fact, when we plug this into our calculator, we get that delta G is about 2.25 times 10 to the 3 joules. So the change in Gibbs free energy for this compression is 2.25 times 10 to the 3 joules, or about 2.25 kilojoules. And this positive sign makes sense. With that, we're going to end the lecture here. In the next part, we'll talk about phase equilibria. I hope this has been helpful. Please let me know if you have any comments, questions, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.